variance with LBAB norm. Okay. Now the question is, if this integral is a random variable, then using this integral I can define a process actually. Okay. So let me define a process. So let's take f, that is, a square integral function, and define a process mt. So mt is what? Mt is the integral of f with respect to, say, AWS from a, to the instant t actually. Okay. Then I can treat mt, okay, if t is from, say, a to b, as a process, as a continuous time stochastic process actually. Okay. So my claim is, and that's what makes stochastic integral important actually. So this claim is a very interesting claim. So the claim is this process mt, okay, B is a Martingale. Okay, Martingale with respect to the filtration that is generated by the Brownian motion. Okay, the trajectories of the Brownian motion, where f is less than or equal to t. Okay. Let's give this guy a name f2. Okay. So it's really a natural filtration to the Brownian motion. Since this integral is something in terms of the Brownian motion, then my claim is that this mt is able to see it correctly. So with respect to calligraphic ft, that is basically the similarly generated by the Brownian motion actually. Why this problem is useful? This it will feel like a stochastic analysis, stochastic calculus actually. So imagine you want to prove some quantity to be a Martingale. So the one way is that, okay, you have this fancy definition, okay, so prove it that it's adapted and integrable and all that, and Martingale property. But the other quite often used trick is that just show that your given process is equal to the integral of, is a stochastic integral actually, for example. Now for the stochastic integral, for example, of, for the f for L2AB, it will prove that, the same result for a bigger class of the stochastic processes. So if a given process is equal to a stochastic integral, almost should be, okay, then that process will be Martingale as well. So you don't have to verify the assumptions of being Martingale actually. Just show it that it's equal to some kind of a stochastic integral. Okay. So why this process that is defined by a stochastic integral or the Wiener integral is a Martingale? So let's think about it. Adaptedness is trivial. Okay, it's not a big deal because this is adapted. I can see this as the limit of the sum of the increments of the Brownian motion. Okay, and the Brownian motion is adopted here, inappropriate manner actually. Okay, so adaptedness is not an issue actually. The real thing would be integrability. But integrability is not also an issue. So if I give you that, okay, what would be, the expectation of mt square actually? So if this is the stochastic integral, this would be same as the equation that we take a to t, okay, and integrate, say, the determinative function f square of f and ds actually, okay, and this can be estimated by a to t f square of s ds, and this is certainly finite actually because f is a. Okay. F is a. Right. So integrability is also an issue. The issue, okay, so you can say for integrability you don't need to show that the expectation of mt square is finite. You need to show that expectation of, so it's integrable, not a square integrable actually. But I know that I have Jensen's inequality that tells me that expectation of mt can be estimated by the square root of expectation of mt square. Okay, so this guy is finite, so this must be finite. Okay. In other words, you apply the Jensen's inequality for phi equal to x squared, so you have this inequality. Have it. This is finite, so this must be finite. Now I would like to show, the Martingale property. The crucial part is really to show the Martingale property. And what does Martingale property says that the expectation of mt given if f is equal to ms be almost sure. Okay? Be almost sure. This is what that I would like to show. Now if I phi mt, okay, I can write mt and obviously s is some instant before the time t. Okay? So mt can be written as ms plus an integral, okay, from s to t, and f of s, f of u, d, w, u, okay. T. And write it like that. So this must be. So what would be the expectation of mt given fs, okay, since the mt can be written as, I'll be happy with this expression. So it's like, okay, integral from, a to t, so we split it into a to s and s to u actually. So this result is also true. Okay, we can ask, is this result true here? And in case of the Wiener integral, the answer is yes actually, which is still valid actually. You can show it easily, it's not a big deal. Okay. So the expectation of mt given fs. So this guy is measurable, ms plus the expectation of this integral s to t, f of u and w of u given s. So you have because ms is fs measurable. So I'll be done with the proof if I can just show that this is 0 p almost surely. So if I can show it, this is 0 p almost surely, I'm done. Okay, so the next name that I have is that this expectation from s to t of u, dw of u given fs is 0. Okay? And this trick through which I'm going to prove it 0, just not only just see this as an argument, but see this as a method actually. So quite often we use a similar kind of a reasoning, when we want to, something like this to happen actually. Okay? So how can I show it? Here's the thing. Now f is from where? F is from L to a b. Okay. So I can find a sequence of step functions. Okay. That can approximate your f in L to a b. Okay. That can approximate your f as m goes to infinity. Now I would like to show. Okay. And what would be, so if I replace this f by, for example, this step function, in other words, we take an abstract step function, say f and u. So this would look like, something like I equal to 1 to n and ai, okay, maybe this is a different index, so fm of u, okay. AI and should be n and what? Indicate a function of ti minus 1 to ti. Okay, so something like this actually. Okay. So what would be the integral from s to t? Okay, for fn of u and dwu. So I can write also this as a sum with the appropriate indices. Okay, I'm not interested in indices. Can I start from s and go somewhere? Or maybe if s lies between, so I can partition this s to t actually, and I can play the same game. Okay, ai, okay, times indicate a function of what? Ti to ti minus 1, not ti, but b of ti minus b of ti minus 1. So I'm a bit being informal here actually, okay, not a bit precise actually, because you can say that, okay, this is the partition for the interval a to b, and now you are integrating over s to t. The answer is that I can find a partition for s to t as well, okay, and let's denote it by the same notion actually, so it's not a big deal. Okay. So being a bit precise actually. So this would be equal to this sum. The question is, what would be the expectation of this for now, for this integral? Think about it. So if I take this and substitute it here, okay, and I substitute it here, so this sum will come out. Okay. And you have AIs that will also come out. The constants would also come out. And you're going to have the increment of the Brownian motion given here. But these increments of the Brownian motion are the increments after the time s actually, because you are partitioning s to t. So it must be independent. And if it is independent, the expectation of v of ti minus 1 would be 0 actually. So in other words, if I replace this with step function, okay, this f with the step function must be 0. Okay, so just showing this argument directly. Are we happy with it? Okay, so I'm saying take this and substitute it here. So the sum would come out, the constants would come out, and you're going to have the Brownian motion, increments of the Brownian motion. But now these ti's and ti's minus 1 are the instants after, are in the interval s to t. So these are independent of fs. So this will be equal to the expectation of the increments of the Brownian motion. Okay.
Cancel out to them.
Cancel out क्यों? Okay. We are too quick. So what I'm saying is that think about this s to t and this fn of u dwu and given fs. And this will be same as sum, and I'm taking this sum out, constants, and I'm taking these constants out. So I'm going to only remain with v of ti, not v, but w of ti minus w of ti minus 1 and given fs. Okay. Now what is this expectation? So it must be 0. Why? Because this is independent of Fs. Okay, so this will be equal to the expectation of WTI minus WTI minus 1, and the expectation of the increment of the Brownian motion is 0, so this must be 0. Okay, this must be 0. This must be 0. Okay? So I want to show this for arbitrary f. But for this arbitrary f, I took a step function, sequence of the step function, which kind of approximates your f. And for these step function, this required inequality holds actually. It's not a big deal. But I want to prove for the f actually. Okay. So you can already see that where I'm trying to go actually. So what I would like to do is that this can be seen as the limit of the conditional expectation of the integrals of fn given fs. And since that conditional expectation of a step function is 0, so the limit is 0 and hence this is 0. That's what I would like to go at. Okay? But that limit must be almost surely. Okay? Because you want this to be equal to P almost surely 0. Why? Because you need this equality P almost surely. Okay? Alright. There's a lot of hand waving, but when I write an argument, you will see that how does it work. Now here's the thing. Here the conditional expectation version of Jensen's inequality. I'm going to use it. So the conditional expectation for phi of x equal to x squared. So I know that for what's the Jensen's inequality for yes. So the Jensen's inequality is also true for the conditional expectation. So if I have expectation given a say sigma field G is same as the expectation of the conditional expectation of the random variable given G actually. So this is true. Okay? Jensen's inequality. Now if I take phi of x to be x squared, I know that the expectation of the square of the conditional expectation is same if can be estimated by the expectation of phi of f of x squared given G actually. Okay? So using this inequality, here's the conclusion that I would like to have. So the expectation of integral from s to t of fn minus f fn of u minus f of u and dwu it's square given fs. Okay. So for me, I'm taking this quantity, this entire quantity as x actually. All right. Put in a square here. So I'm replacing x by what? In this, I'm replacing x by this stochastic integral, which is really the difference of the integral of the step functions and the original function f of x. So this can be estimated by should we have so we should have expectation inside of this y because it's the phi of the expectation of x actually, so expectation should be inside. So this can be estimated by the expectation of so that integral from s to t of fn of u minus f of u and dw of u squared and given fs. Are we happy with it? So this expectation can be estimated by this actually. Okay? So I'm going to make a use of it. Now, let's do now, let's use this property which simply says that if you have expectation of x given g, where g is some sigma field, okay, this is same as the expectation of x. Okay, this is same as the expectation of x. Now I would like to take this side of the inequality and take expectation of it, the left side of it, and apply this property. So I'm going to have expectation of expectation of this integral s to t fn of u minus f of u, okay, d w of u, okay, given fs and bracket closed and it's a square. Okay? So I'm taking the expectation of this. So this will be same as, okay? This will be same as, another thing could be that I'm taking the expectation on the both sides actually. So if I'm taking the expectation on the both sides, what the other side will become?
Only integral term.
So is the expectation of the conditional expectation is going to be simple expectation. So this would be equal to the expectation of this s to t fn of u minus f of u d w of u and the square. So this will be the case. I can apply E to isometry. So what would the E to isometry will turn? So it will turn this stochastic integral into the deterministic integral. Okay. So it's going to be s to t, okay, and fn of u minus f of u square and dt. Okay. Are you happy with this? So this is like your I of f. So yeah.
आइडेंटिटी उसकी है, उसमें x g मेजरेबल
x जो है
g मेजरेबल
इस ऊपर वाले में. So everything is measurable actually. So why should it be this measurable?
तो s से d तक है.
एक मिनट. So do we need measurability? I don't think you need measurability. I don't think you need measurability. उसमें measurability नहीं चाहिए. ठीक है. So you don't need measurability. So again check the assumptions. Check the assumptions. But I'm sure you don't need measurability. ठीक है. So you have it. Now what is this? I can estimate this. So this is the integral from s to t. But I know about these two guys that if these limit would become a to b, this difference goes to 0 as n goes to infinity actually. But this is the integral from s to b, so I can estimate it from a to b actually, by a to b. So which I can say that this would be same as fn of u minus f of u square and d. And this goes to 0. ठीक है? What is the meta conclusion of this? The meta conclusion of this is that this species, like this conditional expectation, if I give it some name, so if I give it a name xn actually, or maybe xn, something like that, because it's something depending on n, this goes to 0 in L2 omega sense actually. So if I give this internal species a name, okay, xn, so the expectation of xn square goes to 0 as n goes to infinity. Okay. So what does this shows? This shows that I can also say this, that is, this shows that the expectation of s to t fn of u, okay, dw of u given fs converges to the expectation of s to t f of u dw of u given fs, but in L2 omega sense. Okay? L2 omega sense. इसके 0 में जाने का क्या मतलब? यही मतलब है. ठीक है? You have it actually. Now, the convergence in L2 omega implies the convergence in probability. Okay? So it implies the same convergence in measure. Okay? The same two quantities. But you don't need this convergence in probability or the convergence in L2 omega, you need the convergence almost surely. Okay? So the argument is we want almost surely. So do you remember a relationship between the convergence in measure and almost surely? You can't drive it. You can't show that the convergence in measure implies, almost everywhere convergence. Okay, I mean, if you have an abstract measure, convergence in measure does not imply almost everywhere convergence, and hence convergence in probability does not imply almost surely convergence. But what it implies is that you can find a subsequence, okay, of this process, which is going to converge almost surely to this actually. Okay. So this implies that I can find a subsequence, okay, of, say f and k, okay, such that, you have this convergence, maybe you have this, that limit n goes to infinity, okay, limit n goes to infinity, this expectation of s to t f of u dw of u given fs is equal to this इधर n होना चाहिए, expectation of s to t f of u dw of u given fs almost sure. ठीक है? Now, I can put an nk here. No, I know that this is 0 for sure. Why? Because this subsequence is really this, subsequence of this sequence, and for this entire sequence we have proved, okay, that such an integral is 0 actually. So what does this shows? That this guy equal to 0 almost surely, and that's what you wanted actually. That's precisely what you wanted, that this must be equal to 0 almost surely. ठीक है? Shall I give you a, repetition of the trick, the bigger picture of the trick actually. So you want to show that this is equal to 0 or be almost sure. So what did we shown? That since f isn't from L to AB, I can find an approximating sequence actually.